practicing for the quiz next week. Okay, so here's what's the input of sine? What's the input of sine? Huda? Measure of the angle, swept counterclockwise with a 3 o'clock position. Okay? And so if we were grading this right here now, measure of the angle would be worth 1 point. Swept counterclockwise would be one point, and from 3 o'clock would be 1 point. Those are all essential details. If it's a clockwise angle, it won't be the input for sine. Okay? If it starts from somewhere else besides 3 o'clock, it sweeps, from midnight, from noon, or from 8 o'clock, it's not the sine. The input of sine has to be this angle. This angle, so counterclockwise from 3 o'clock. Con?
What did you say? Equal square?
It's so the input is the quantity, the measure of the angle. Just angle is the object of the two rays, right? So it's not a number. We're not grading this now, but to be precise, the input of a function is a quantity, and an angle itself is not a quantity. The angle is the two rays that join at the vertex. So we need the quantity to be the input. That's the measure of the angle. Okay, what's the output of sine? What's the output of sine? Are we learning this by now? Yeah, Anna.
The vertical distance above the horizontal diameter in radius.
Perfect. Vertical distance, 1 point. Above the horizontal diameter, 2nd point. Must be, it will always give you radius lengths. What's the maximum that could be?
1.
And where is it 1? Where on the circle?
On the right.
Oh, the sine. Sine. It's the vertical distance. Where's the vertical distance? 1 radius length. Pi halves are at the top of the circle, right? So if 1 is the maximum value, then another way to think about sine is it's like giving you the fraction of the radius that you are up, right? Because 1 is the most. So anything else is going to be less than 1. So it's going to be like 0.5 or 0.2 or negative 0.3. So it's another way to think of sine is it's a fraction. What fraction of the radius are you above the horizontal diameter? Okay? And the unit circle coordinate? Up and down coordinate is y. Okay, input for cosine. Exactly the same as sine. Got to have all the details. Measure of the angle, swap counterclockwise from 3 o'clock. Cosine now. What is cosine? Oops, I actually clicked it. So that's the horizontal distance right of the vertical diameter. That's going this way, right? And that's the x-coordinate. So this will be the first half of your quiz next week. And everyone's going to get 100. Okay, so I do these quizzes. The point is not that I want you to be able to memorize these definitions over here, and then I want you to be able to work problems and do math, quote unquote, over here. The whole point the reason I have you do these is that when you come to problems, you want to apply your knowledge of these ideas to solve the problem. So if it's asking you for sine or it's dealing with sine, then you think to yourself, okay, what is sine? Sine is the vertical distance above the horizontal diameter, and how does that help me solve this, right? Or they might start talking about, in a question, what's the horizontal distance to the right of the vertical diameter? And then you think, oh, I know what that is, right? That's cosine, okay? So it's not two separate things that I'm trying to teach you, like to memorize some definitions and then to be able to do some procedures. So it's these ideas, knowing these ideas, that will enable you to best solve any kind of problem, right? Not just certain ones that you've memorized, but if you know this stuff, then you can come to varying situations and make progress. Okay? So keep remembering that the point of the quiz is that material is what you're using to solve the problems. Okay, questions about these definitions? Okay, and then just as a quick, all right, so let's do these. So go ahead, everyone. Let me draw this here. So here's, so go ahead and estimate sine and cosine for the current position of the bug. Estimate sine and cosine using the definition, right? So using the definition. And estimate the angle too. So let's estimate angle in radians, sine, and the cosine. Based on getting it. All right, what do we think? What would be an estimate for the angle? Austin, can you make an estimate for the angle? How many radians would that be about? He's saying 2.4. Reasonable estimate? Yeah, something, 2, a little bit greater than 2. Yeah, so 2, anything from maybe 2 to 2.4 would be fine. Something a little bit greater than 2. Okay, what about the sine of theta? Huda? 0.8? She said 0.8. What do we think? So do you see that that's like what we're asking, what fraction of a radius are you above the horizontal diameter? So that's like 8/10, right? 8/10 of the way up, or 80% of the way up a radius from the horizontal diameter. All right, what about cosine? Con, did you get cosine? Estimate? What's that? Negative 0.6. What do you think, Omar? Negative 0.6. Why not?
Because it's above the horizontal axis.
I asked for cosine.
No, cosine. It's negative 0.3.
Negative 0.3.
That's on the left, and it's it's not close to 1, so.
But 0.3 is less than 1/2. 0.6 is greater than 1/2. Right? 0.3 would be before you got halfway, and 0.6 would be after you got halfway. So I'm liking negative 0.6, because it's a little bit further than halfway, right? Do you see that?
Okay.
Halfway is about here, and he's saying it's a little bit further than halfway to the left.
But isn't it like, I got lost because of the horizontal diameter, if it's above the horizontal, but we're not talking about the horizontal diameter.
Cosine.
Cosine.
What is cosine? The horizontal distance to the right of the vertical diameter. So it's measuring this way.
Okay. Oh, okay, I see. I see now.
So it's this, cosine is represented by this length right here. From there to there. That's cosine. The horizontal distance. Sine is the vertical distance from the horizontal diameter.
Okay.
Is it better?
Now I get it, because I used to get mixed up.
Yeah, so that's why we're taking the time to let's get this straight, and we'll practice it. Okay, other questions or questions about this? Okay. All right, so then just quickly, we'll just review graphs of those. Just take a look. So the sine graph, okay, would be what? So when we graphed the covariation of these, we looked at angle. We put this angle, measure the angle swept counterclockwise from 3 o'clock. We put that on the, so rather than have it being sweeping around the circle, now we're stretching it out straight on the horizontal axis. So increasing angle is to the right on the horizontal axis, and then we can, on the vertical axis, we can put the vertical distance above the horizontal diameter. So in the first quadrant, as we change theta from 0 to pi over 2, what will the sign do? It will change from what to what, Brooke? So, 0 to 1, because it starts at the horizontal diameter, and then its vertical distance above the horizontal diameter goes up to 1. And we talked last time about why that's concave down, right? The changes are getting less positive, so it's a decreasing rate. If that sign is increasing from 0 to 1. And then in the second quadrant, the sign, as theta goes from pi over 2 to pi, what does the sign do? Tim, goes from what to what? Just the value of the vertical height. So the vertical distance will go from what to what? 1 to 0. Right? It starts at 1 at pi over 2, and then it decreases to it decreases to 0 once you get to pi, because we're not above at all, right? We're at 0. Okay, third quadrant. Taz. So what does the value of sine do as theta goes from pi to 1.5 pi? Goes from what to what? Yeah, so this. So as the angle increases from pi to 1.5 pi, what does the sign do?
Do you want to know what the graph is? Or
I want to know what the value of the sign does. Change. 0 to -1. Okay? And then Justin in the last quadrant. So as the angle goes from 3 pi halves to 2 pi, what does the sign do?
-1 to 0.
Right, -1 to 0. And so that's just for one rotation. So if we continued for values greater than 2 pi, all those same output values would reoccur, right? As if we did one more rotation, we get all those same output values. So this is what's called a cyclical graph, okay? And so this is one cycle of sine. One cycle of sine theta. And so we see this. As the angle increases, what does the bug do? It goes up to the top of the fan and then back down to the middle of the fan when it's at pi, and then down to the bottom, lowest point of the fan, and then back to its starting point. So as the fan goes around, the bug goes up, and then all the way back, all the way down, and then back to the middle. And so that's what sine is showing us. But it doesn't matter how big or small the circle is, because what is this maximum value? What's this maximum value right here? 1. And 1 what? Radius length. So this is universal. Sine is universal for all circles. Because no matter how small the circle is, you get to the top of that circle, it's going to be 1, because it's going to be 1 radius length. Same with the bottom, -1. Okay, quickly we'll do cosine again. So in the first quadrant, so cosine again means, what is the meaning of cosine? Jared? What does cosine give us? Good. And so in radius lengths. And so from 0 to pi over 2, what does that quantity do? It goes from what to what? 1 to 0. Starts at 1, and goes to 0. So this is a little trickier because we're putting the horizontal distance now on the vertical axis. So that's why it starts up here at 1, because that horizontal distance started at 1. Still same measure of the angle swept counterclockwise from 3 o'clock on our horizontal axis. Okay, in the second quadrant, what does cosine do? Hamid?
From 0 to -1.
0 to -1, because it's moving now toward away from that, it's moving to the left, away from the vertical diameter. And so now it's -1 to the right of the vertical diameter once you get to pi. Okay, third quadrant. Jonathan. So as the angle goes from pi to 3 pi over 2, what does cosine do?
This is 0.
From what?
From
-1 to 0. So now that horizontal distance is back at 0. And then in the fourth quadrant, Alex. Yep, the horizontal distance is 0 here. And then as he returns to the starting position, back at 1 unit, radius unit, to the right of the vertical diameter. So this is one cycle of cosine. Again, if we increase the angle past 2 pi, then we get a repetition of these same output values, right? Every time we go around the circle, we'll just get these same output values over and over again. So if we graphed more theta, we would just see this thing repeating over and over again. Okay, so that's our sine and our cosine graphs. So you had in your web work, you had this deal, right?
Oh, yeah.
Let's practice here. So, so it says that the radius is 36.5 at the ends of the circle, or at the ends of the track. There's semicircles with a radius 36.5. And so let's just go right to number 2. So suppose the runner runs 15 meters in the first lane. The question is, what angle in radians does that represent? So what angle in radians is associated with that arc length? So no calculators. Put your calculators away. Everything we're going to do here is we're going to write out expressions. And then we'll get our calculators out later. So just no calculators. How would you describe, or how would you write an expression for the angle associated with this 15-meter little segment? Somebody new. Audie. So what angle has he run through?
To find the angle, you put his distance over the distance of one radius length.
Okay.
6.5.
So he
That's
wants.
his radius. That fraction.
And why does that work? So why is that giving you the number of radians?
Because a radian is one radius length.
Okay.
So if he's run that fraction of it, then that'd be a fraction of the radius.
Good.
Radian.
Yeah. So this is a fraction of the radius length that he's run. And so therefore it's the angle in radians. Nice. Okay. And so then what about his coordinates? So he's run 15 meters. What are his coordinates at that moment? So how can we get the x coordinates? Brian.
We do cosine of 15 over 36.5.
Okay. And what is that? Cosine of 15 over 36.5, you're going to get a number. So can you explain what that number would be when you did the cosine of 15 over 36.5?
That number would be the fraction of the radius length.
Good. He said it's a fraction of a radius that he is to the right of the vertical diameter. What do you think?
Yeah.
Well said. Yeah, that's going to be some fraction. And now estimate that. So let's estimate that value without no calculators. What do you think that would be? Right here, Patrick. Can you estimate what fraction of a radius he is to the right?
Just short of half.
Just short of half. What is cosine again?
Cosine. Almost 1, so it would be 0.9.
If you were thinking in 0.9, 0.95, that's in the ballpark. Almost, even though he's run 15 meters, mostly he ran up. So he's still almost a whole radius length to the right. Okay? Because most of his running in that first 15 meters was up. So he's still almost a full radius length. We could drop this down here. You know, he's really this far, he's still this far to the right of that vertical diameter. Okay, what about the y-coordinate? How about Jared number 2, Jared Smith? What about the y-coordinate?
It would be sine. Sine of 15 over 30.
Right, sine of the same angle. And can you make an estimate for that? He wants 0.4. Reasonable? Yeah. Short of halfway up. Okay, so we got these coordinates, 0.9, 0.4. Any comments? 0.9, 0.4. Are these the runner's coordinates? Alex?
Right now we have them in measurements of radius lengths.
Right.
Right? Or we actually want that coordinate, wouldn't we have to take into account the fact that the radius is 6.5 meters?
Okay.
So you would have to multiply your cosine and your sine by that radius length.
Okay. Okay. So these are valid coordinates if our graph, if this point was what on our graph? 1, 0, right? So if this was the point 1, 0, then we would have the valid coordinates for the runner. But since we're showing right here that it's 36.5, that gives us that's kind of defining our scale here. Are these coordinates correct with that coordinate, starting coordinate being 36.50? So Alex is saying if it's 0.9 of a radius length, how do we get it in meters then? Multiply it by 36.5. So it would be 36.5 times cosine of 15 over 36.5. So that'd be the x-coordinate and then the y-coordinate. All right, so now get out your calculator. Let's take a look and see how we did on our numbers. Now so the estimate is based upon my guess at where 15 meters are. I'm not guaranteeing you that's 15 meters, so hopefully it's in the ballpark. All right, so first find cosine, or first make sure your calculator's got to be in radians. So somewhere there's a setting, most of you have the TI menu, mode. Third thing down, make sure radians is selected. Go back to your main screen, and you're going to put in cosine, hit cosine, and then 15 over 36.5. And is it something close to 0.9?
Yeah.
What is it, Walter?
It's 0.916.
916, good. So I got a good picture here. So I picked a good spot matching up with 15 meters, okay? And so now, what would you just, before we do this, what would you guess it to be in meters? So how many meters to the right is he? Would you just make a guess? 32, 33, almost 36.5. So now how would you get that? Yeah, you're going to take that fraction, that 0.91 or whatever that cosine was, now multiply it by 36.5. And that'll give us it in meters.
33.46.
33.46. Okay, so let's practice again with your calculator. Find the sine of 15 over 36.5, and we're thinking that's about 0.4. Find your 0.498.
4.98.
It can't be 4 points.
The sign is, well, if you multiply it by 36.5.
I just want the sine right now. 399. Look at this. You guys are awesome. 0.4 is our guess. We got 0.399. And then the actual in meters, less than half, little bit less than half of this, right? So the actual coordinates then, given this 36.50, these are the coordinates. Had that been 1, 0, then it would be the 0.9 and the 0.4, or the point, whatever these were. Okay, so I want you to repeat number 2 for 82.5. 82.5 meters, and I'm gonna guess again where that is. Hopefully I'm in a good spot here. Let's see. So 82.5 meters is going to be, I'm thinking something like that. No, or less.
Radius remains the same, right?
Same situation. It's just from the start, run 82.5. So no calculators at first. Sorry. So do the whole thing without your calculator first. Get an expression for the we gotta understand it so we know what we're doing when we use the calculator. So estimate or not estimate. Get an expression for the radians. Set up the coordinates. Okay. Write it out. Write it out. I'll do this one all in red now, just so we have a difference. All right, so angle, Christian.
The angle is 87, or is that 82.5? Yeah, 82.5 divided by 36.5.
You tell me why that gives you the angle in radians.
Because the arc length ran by the runner is 82.5,
Okay.
and the radius length is 36.5, so if you divide the amount ran by the radius, you should get the radius.
Right, so that you're taking 82.5. We're asking how many 36.5s or how many radius lengths fit into that, right? How many radius lengths or how many 36.5s fit into 82.5, and that will be the same as the radians. Okay? X coordinates. Morgan. Yeah, let's do final coordinate in meters. Okay, so what about just the cosine itself? Can you make an approximation for the cosine itself right there? If this is the right place. I'm not sure it is, but negative 0.6. How's her estimate for negative 0.6? Good, okay. And then y coordinate? Diana, did you get the y coordinate? Meters. And can you estimate the sign right here? Where I have the runner? I don't know. 0.7. Yeah, 0.7, 0.75, yeah. Right there. 3/4 of the way up. Okay, how about did anyone get these meter values? Let's see how I did. So, anyone get these values? Just do the cosine and the sine. Just put in the cosine and put in the sine, and we'll just see if he's in the right spot, okay? Yes, yes, I missed, yeah. One approximation now. So what does the cosine say? Negative what? 0.63? I made a good guess. Looks reasonable, right? A little bit further than half. Okay, and what does the sine say? 0.77. And so then, since those are fractions of the radius, multiplied by 36.5 gives us those same equivalent in meters, and that's his true coordinates. If we have this reference here, 36.50, these coordinates are in meters. Okay, cool. Feel like you guys are getting it. Picking up on this? Okay. And this is arguably the most important thing of all of trig, because all of trig is based on this. All of trig is based on meanings and the setup of the circle and the meanings of sine and cosine. Okay? So let's, any questions? Anybody have a question? Let's take a look at this. Yeah, please.
How come they don't teach you about this in high school?
That's not a quick answer. That's a conversation. But glad you're here. This is a cultural thing in our country, like what math has become in our country, right? So this is a culture, and so we're committed to pursuing the actual ideas and what's the meanings behind everything. Okay, so we're gonna keep doing that. All right, so here's where it began. What am I showing here? What is the idea behind what I'm showing here? One radius length wrapped on the circle, therefore an angle of 1 radian. Okay, so that's where it all began. Okay, and so from that we could easily get, whole values of radians. So we could go 1, we could go 2. And then 3 and 4, and these spots mark off amounts of openness that give us whole number of radians. Okay? And we were interested in halfway around the circle. So if this was 3, it was 3 to here, and we said it was a little bit more than 3. And how much was it exactly? Pi, right? So pi was this number of radius lengths to get halfway around the circle, so it's the measure of an open angle. So open or straight angle, right? Straight angle. Straight angle is half a circle. Okay, so that has a measure of pi radians. So in terms of finding other key angles in the circle, are we going to use pi or are we going to use our integers? So if we want angles that have symmetry with the axes, are those going to be based on pi or based on these whole numbers of radians? He says pi. Agree with that? Yeah, because these whole number of radians, they just end up in kind of like random places. Not random, but places that don't have any real symmetry with our axes. But pi is halfway around. It's exactly here at the very left end of the circle. And we know 0 here is at the right. So pi is what we can use to get some symmetric angles. Okay, so the first is from pi we can cut the circle up into, say, first 4 pieces. So we'd have pi over 2 at the top, 1.5 pi at the bottom, and 2 pi all the way around, and then we could cut it in half again. So we'd be dividing the circle up into 8 equal angles, and what would one of those be? What openness would we have for one of those? Okay, but we're not doing with degrees. Right? So what amount of openness would 1/8 of a circle have? Jaden?
That'd be
Pi over 4. So pi over 4 is the amount of openness in radians. It's cutting off 1/8 of the circle, exactly 1/8 of the circle. So if it's pi over 4, then we can get all the, since we keep going by pi over 4, we can just get the rest of them by counting. All we have to do is count. So there's pi over 4, and we can just count. 1, 2, 3, 4, 5, pi over 4, right? So there's 1, 2, 3, 4, 5, 6, 7, 8. So all you have to know is that pi over 4 is 1/8 of the circle, and then you have to know how to count. And then you've got all the pi over 4 angles. Now, the ones that we already knew at the top, at the left, and right, and the bottom, those should agree. It's just that now they're now in terms of fourths. So this is still pi over 2. This is still pi. This is still 1.5 pi, and this is still 2 pi. So what we get is we get 4 new angles that we didn't know before. Those 4. So we get this pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, and we can do it again. We can split the whole circle up into, or the top half into 6 pieces. Okay, so we're going to take that top half of the circle and split it up into 6 pieces. And so then what fraction of a circle is this right here? So if I draw this. So 2 questions. What fraction of a circle is that? And how many radians of openness is that? So answer that with the person next to you. What fraction of a circle is that? And what angle in radians is that? Okay, so what fraction of a circle is that? Huda. She wants 1/12. Agree with 1/12?
Pi, 1 pi 12.
1 pi over 12.
Yeah, I mean, for the opposite. 1/12 times pi.
1/12 pi. So I'm asking for what fraction of the circle is that? Alex? What fraction of the circle? Well, now you're saying 1/12. You saying 1/12? It's 1/12. Okay? Because if it's 1/6 of half, so we started by saying we're going to take the top half, break it up into 6 pieces. So that breaks the whole circle up into 12 pieces like that, right? So that's 1/12. And what is that angle? Pi over 6. Okay, so now all you have to know is if you break it up into 12 equal pieces, then you just, all you have to, again, all you have to do is count. You just count pi over 6s. So there's 1 pi over 6. Here we go, ready? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that again repeats our top and bottom, left and right, and that we should just verify that they're right. 3 pi over 6, that's our pi over 2. 6 pi over 6 is pi. 9 pi over 6, 1.5 pi. 12 pi over 6 is 2 pi. So the top, bottom, left, right is fine. And then we look at the new ones we've got here, and we notice that these ones closer to the top can all be simplified into thirds. Okay, those can be simplified into thirds. The new ones here that are more out to the sides stay as sixths. Okay, so we get this new set of 4 angles that are thirds, and this set here that are sixths. So let's change them to thirds. So I just changed the ones more towards the top. Those are thirds, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And then there's the ones we already knew, 0, pi over 2, pi, 3 pi over 2, 2 pi. So here's what we call the 16 key angles of the circle. Okay, so this gives us 16 angles based on symmetry with the axes. Okay, so how many angles are there from 0 to 2 pi? How many angles are there? As many as you want. Are there 16?
There's much
Should we
more.
have more?
How many angles are there from 0 to pi over 6? As many as you want. As many as you want, an infinite number. Okay? So the reason I point that out is because sometimes the students latch onto this circle and then their whole universe just becomes these 16 angles. And it's like there's no other angles that exist. So we throw a point on the circle and they immediately they're trying to put that point on one of these places. Okay? So if you just have a circle and there's nothing about key angles and you put a point on it, it's like all the examples we've done before. We're estimating, maybe we're estimating the angle, maybe we're estimating its vertical or horizontal distance, but it's not necessarily one of these 16. In fact, if you randomly picked an angle, the probability that you get one of these is 0, because there's an infinite number of other angles besides these 16. Okay, so it's just that these have nice symmetry with the axes, but there's just know that they're not the only 16 angles, right? There's an infinite number of angles on the circle. Okay, so we want to talk about sine and cosine of some of these key angles. So we're gonna stick in the first quadrant here, and so let's look at we're gonna look at pi over 4. So we're gonna put our focus on pi over 4. So let's first start by, just want to show you. This is a little small. I'm going to rewrite. Here's a scale. So first I want you to estimate the sine and estimate the cosine of pi over 4 just by looking at the picture. Okay? So estimate the sine, estimate the cosine of pi over 4 just by looking at the picture. Okay. Nina, what would you estimate the cosine to be of pi over 4 by looking at the picture? 0.7. She said a 0.7. What do you think? Yeah, so here we see that its horizontal distance to the right is right pretty close to 0.7. What about the sine? Same? Looks about the same. So there's our estimates. Are we good? Everyone agree with that? Okay. Now we want to find them exactly. We want to find those exactly, so we need geometry. So we need some geometry to be able to come up with those values exactly. Any ideas? How can we use geometry and we want to get precisely what cosine of pi over 4 and sine of pi over 4 are. Morgan? Oh, I thought you said something. No. Haman?
Divide 4 by pi, and then take that number and then find the sine of it.
You want to divide what by 5?
Pi by 4.
So you want to take pi over 4 and divide that again by 5?
No. 3.4. 3.14
Okay.
divided by 4.
Okay.
And then take that number and then find the sine of it.
No, but we're actually we want to find the sine. That's the point. We want to know, see, this is just an estimation. We're trying to come up with a geometric way to truly get the exact value. So, any ideas? How can we use geometry? Nina?
Draw a right triangle and use the Pythagorean theorem.
Okay, so tell me what right triangle you want to draw.
From the center of the circle to pi over 4.
From here?
Yes.
Up to pi over 4?
And then now you have a right triangle, and we know that the hypotenuse is length of 1 because it's the radius of the circle.
Okay, so she's saying we just made a triangle, and that length right there, which should be straight, is 1. Okay, and so we got a right triangle right there. Do you see it?
That should be 45 degrees.
So what does this right triangle have to do with cosine and sine of pi over 4? What does that right triangle have to do with cosine and sine of pi over 4? Yeah, go ahead.
Cosine would be the x coordinate of the point. and
So
sine would be
if
the
cosine's
y
the x coordinate, what does that have to do with? This is cosine, right? Cosine pi over 4 and sine pi over 4. Those are coordinates. What does that have to do with the triangle? So that x coordinate, what does that have to do with the triangle?
That would be the base of the triangle.
He's saying this is the x coordinate, the base. Yeah. So we could label it cosine pi over 4 because that's what it is, or we could just call it a, just because it's easier. Just call it a. So our a is cosine pi over 4. What does sine pi over 4 have to do with this? Taz.
Sine pi over 4 is the y value.
Okay, it's the y value. And what does that have to do with the triangle?
If you use Pythagorean theorem, that's what will give you the y value.
But what does the y value of this point have to do with this triangle?
It's that side, like the opposite.
This one?
Yeah.
You're saying it's the length of that side? Yeah. So we'll call it b. So they're talking about, so if we want to get the cosine, we're trying to get a, then we have a squared equals, or a squared plus, b squared equals c squared, and c is 1, so 1 squared. Okay, but that's two unknowns, so it's not enough information. Any ideas? Trying to get a, or we're trying to get cosine pi over 4. Joe, any ideas? No? Tim, any ideas? How can we, so it's too many unknowns, so we need more information. Shola, is there anything we can do here? Okay, what? What do you want to substitute? Okay, so that's cosine pi over 4, and then? Okay, that's true. So we could put in cosine pi over 4 there and sine pi over 4 because that's how we defined them. But we still got these two unknowns in that equation. So what are we going to do about that? There's something special about what's going on here that we haven't used yet.
Pythagoras?
No, that's Pythagoras, right? That's that. So what's special about this scenario that we haven't tapped into yet?
I think you know it.
Audie, what do you think?
No, seriously, you said right now with the angles. No, you did.
All right, Alex, what?
We were just talking about how the right triangle has, your 90-degree angle, and then you have the other two that are the same.
Right?
And maybe if you use those angles to figure out one of those angles.
Okay, well, so we know this angle. What is this angle?
35.
No, not 45. I mean, yes, but not our context, right? What is this? Pi over 4, which is, yes, that's 45 degrees. But try to get away from your default always being degrees, okay? So pi over 4, that's the angle we're dealing with. Okay, so what are we not using still? The fact that what? Nina, what were you going to say?
I was going to say that cosine of pi over 4 and sine of pi over 4 are the same.
And how do we know that? Or why do we suspect that?
Because I don't know how to put this in terms of
Okay.
radians.
What were you going to say?
Well, they're at the same distance from the y value and x value.
Okay, so yeah, it seemed like we approximated them to be the same. And what's special about pi over 4? So pi over 4 is a special angle in the first quadrant. Splits it right in half, right? So because we're exactly kind of halfway up in the first, we're not halfway up, but we've swept half an arc, half of a quarter circle. We're in this nice symmetric place where indeed the cosine and the sine are the same. And that's because pi over 4 is halfway up the arc to pi over 2. So therefore, we can change this to a squared plus what? Yeah, a squared, because they're the same, right? So a and b are the same for this particular angle. And now we can solve it, right? So we get 2a squared equals 1, a squared equals a half, and a equals square root of 1/2. Okay, so put that in your calculator. Square root of 1/2. What are we expecting to get? Something like 0.7, right? We're expecting to get something like 0.7, our initial guess. So square root of 1/2. 0.707 ... right? On and on and on. Okay, so normally though we don't see it in that form. So if we were to rationalize the denominator, that's the same as square root of 1/2 is the same as radical 2/2. We're not gonna, so that's just some kind of pre-algebra with radicals, okay? So the square root of 1/2 is the same as square root of 2/2. Okay, so we just got the cosine and the sine of pi over 4 because we know they're the same. Square root of 2/2 and square root of 2/2. Okay, any questions on that?
Why aren't you keeping it as square root of 1/2?
It's just kind of a form thing. It's not good form to have kind of a radical in the denominator. So it's just kind of math convention to always have not have a square root or some irrational number in your denominator. So you'll see it this way much more often than that way. Okay, so what about pi over 6? So can I erase what's up there? Any questions? All right, so what about pi over 6? Put you to work here. So let's first estimate the coordinates, or the cosine and sine. So we got, what's our x-coordinate? How can we, exactly what is our x-coordinate? How would we write an expression for the x-coordinate? Jaden? Cosine of pi over 6. And the y? Sine of pi over 6. Okay, so there's the exact values, but we want to get what those are, right? So we want to get what those are. And so let's estimate first. So estimate for cosine. Again, this is 0.6. This is 0.8. And this is 1. So estimate for cosine of pi over 6. How about Brian back there? 0.85. What do you think? Yeah, pretty decent. It's like halfway from 0.8 to 0.9. Okay, estimate for sine.
0.5.
What do you think, Corey? Can you estimate sine of pi over 6? 0.5. Okay, so here's the deal. I'm going to tell you that sine of pi over 6 is exactly 1/2. It is exactly 0.5. So sine of pi over 6, not approximately, it is 1/2. And now I want you to find, no calculator, so practice what we kind of just did and see if you can find what the cosine of pi over 6 is. Okay, you're going to work on this. If you followed what we just did, now that I gave you that, sine of pi over 6 is 1/2, you should be able to find cosine pi over 6. Go, you do it.
Did we just figure that out?
No, we found out the cosine and sine of pi over 4. Those were both radical 2/2 or about 0.7, right? Now we're doing pi over 6. we guessed that the cosine's about 0.85, right? So I want you to find it exactly. Given that sine of pi over 6 is exactly 1/2. Should all be able to do this. Geometry. So it says use fractions. So use 1/2. Don't use 0.5. It'll be more convenient. Okay? Use 1/2, not 0.5. That's good. That's the interpolator. Good. What did we do last time? Good. Okay. Right. There we go. So you got some. Good.
Good job.
Oh, so you might do that. We just wrote this triangle now, right? So can you imagine the triangle you have to draw? Label what you got and solve for what you're trying to find. So you should have made this triangle. That's the triangle you should have made. And what sides do we know? Joe, do we know any sides? Which ones do we know? Do we know the lengths of any of these three sides? The radius is 1. Is 0.5. And this is the one we're trying to find, right? Yeah, so we got that vertical side as 1/2 because I told you. And then the hypotenuse is still 1 because it's still the radius out to the circle. And so you get a squared plus 1/2 squared equals 1 squared. When you do the math, you get a equals the square root of 3/4. Okay, and that's the same as the square root of 3 over the square root of 4, or the square root of 3 over 2. Put that in your calculator and you get 0.866 ... which agrees with our initial estimate. Which agrees with our initial 0.85. Okay, so pi over 3 So by symmetry, so pi over 6 is 1/3 of the way along the arc, and then we go another 1/3 of the way, and then to there. So by symmetry, yeah, it's just, well, it's not a good hypotenuse day. All right, so let's just do this. Whoa. Oh. All right, so look, at pi over 3, cosine is half. Sine is it's that same number, okay? Because it's just this, the triangle just flipped up. So if the triangle's down here, it's the same triangle just flipped up here. So what happens to the x and y coordinates, or what happens to the cosine and sine? They just switch. So here's what we found. Okay, this is what we found. We found that the cosine of pi over 6 is radical 3 over 2. The sine of pi over 6 is 1/2. And then the sine and the cosine of pi over 4, they're both radical 2 over 2. And then the cosine and sine of pi over 3 is 1/2 radical 3 over 2. And of course, so how about what's the cosine of 0? We better know these. What's the cosine of 0? Anna? Cosine of 0. Cosine of 0 is 1. And what's the sine of 0? 0. And what's the cosine of pi over 2? And the sine. So we better know those. Okay. All right. So this is the cosines and sines, or the coordinates of the key angles just in the first quadrant. But by symmetry, we just got them all, right? Because by symmetry, the distance above or below the horizontal axis is the same. It's just that if we're to the left of the vertical axis, then all those x-coordinates will be negative. And if we're below the horizontal diameter, then all those y-coordinates will be negative. So basically, we just learned all of them. You just have to apply the right positive or negative. And knowing what cosine is. Cosine is horizontal distance to the right of the vertical diameter. And vertical sine is vertical distance above the horizontal diameter. Okay, so for instance, what's the cosine of 5 pi over 6? So here we are at 5 pi over 6. What's the cosine of that value? Brooke? Okay, so we're going to use these now, the exact values. Yeah, so it's going to be, so the distance that we go to the left here at 5 pi over 6 is the exact same distance that we went to the right at 5 pi over 6. So it's going to be negative radical 3 over 2. What's the sine of 11 pi over 6? Come. So sine of 11 pi over 6. Positive 1/2. Agree with that? The sine. Negative 1/2. So it's going to be the same as pi over 6, but negative. See that? Okay, so why don't you practice answering these others? So if you didn't follow what we just did there for 5 pi over 6 or 11 pi over 6, cosine of 5 pi over 6, sine of 11 pi over 6, catch myself, catch Megan as we come around. Does it make sense? So all we have to do is use this first quadrant coordinates and apply the right pluses or minus based on our understanding of what sine and cosine are, right? Vertical distance above, horizontal distance to the right for cosine. Okay, so work on the rest of these. doesn't make sense, get help, okay? Ask one of these. Tell me, what's the cosine of pi over 3? Cosine.
Second one, it's not both, just the cosine. Cosine changes, it's the sine, but
Yeah,
sine doesn't.
and the sign stays the same, but they're the same height.
I'll do that. So what about cosine of 3 pi over 4?
Yeah, the third quadrant was also comes from
Cosine of 3 negative.
Oh, wait, no.
So that's
11.6, that would be, yeah, the first would be, yeah, cosine should be positive and sine should be negative. But it should be the same under the value. Yeah, it should be pi over 6, but the cosine is negative. The same values of sine pi over 6. It's just that sine is negative and cosine is positive.
They're the same distance.
Yeah, doesn't make sense. It's exactly. I mean, if you look at the pi over 6, all quarters of that rectangle should have the same value, but different signs. And it's the same for the other. Exactly the same.
So those are all the numbers we're gonna.
Yeah, I just remember.
Right.
Renumbered it not to.
You just have to know what cosine means, what sine means, and then how to apply the right positive and negative. Yeah. Any questions on 1 through 6? Requests? Okay, how about what angle gives a sine of 1/2? What angle gives a sine of 1/2? Morgan. Morgan, what angle gives us a sine of 1/2? Oh, okay, sorry. Can you still do it on the fly? Pi over 6. Agree with that? Alex? Isn't there another one? What is it? Yeah, that's kind of the key to this question, is that if you pick a coordinate, so if you pick an angle, that gives you just one x coordinate and one y coordinate. But if you pick a coordinate and ask for the angle, then there'll be 2 times, unless it's one of these 4, top, bottom, left, right. Any other coordinate that you pick, there'll be 2 times around the circle where it'll hit it. So pi over 6 and 5 pi over 6. Make sense? All right, so what angle gives a cosine of -1/2? What gives a cosine of -1/2? Walter. What angle gives a cosine of -1/2? 4 pi over 3? Cosine of -1/2. So 4 pi over 3? And what else? 2 pi over 3, right? So here's our -1/2 for cosine. So 2 pi over 3 and 4 pi over 3. Okay, so the second half of your quiz next week, let's see if I can find it fast, is just a blank one of these. And you're going to fill in all the 16 key angles and radians, the 16 key angles and degrees, and all the coordinates. Okay? But if you kind of follow my approach to this, you just have to memorize a couple things and then everything falls into place, right? So you're not memorizing 110 symbols and where they go. If you understand the first quadrant and then the symmetry of it, you just can write it down. You just create it on the fly. So let me see if I can find that so you know. If you can quietly pack up, and I'll. Okay, there it is. So the second half of your quiz next week will be this. And you're going to fill it in. Radian measures, degree measures, and all the sines and cosines. As usual, I'll post the whole quiz for next week. I'll post that with your homework. Okay, there will be web work, and check Blackboard for homework, but the web work will be slightly delayed. It will be up either tomorrow or Saturday, okay? But we will have web work.